8.1 Monomials and Factoring. And the reason they bring up factoring is because that's really what this whole chapter is about. And so at the start there's prime and composite numbers. So this will just serve as a real brief friendly reminder of what those are. A whole number greater than 1 for which the only factors are 1 in itself is called a prime number. And the concept is nicely shown by doing 1 times 7 equals 7, because the only way that I'll get the number 7 is by multiplying 1 and 7. There's no other way of making that happening. So if I tried to do 2, I'd have to do 2 times a decimal to get 7. So the only way of multiplying two whole numbers to get that, that's what's going to make that a prime number. Compare that to a number like 8, which I can get from 1 times 8 and 2 times 4. So that would be an example of a composite number. Note that the only neither numbers are 0 and 1. 0 and 1 are neither prime nor composite. And just as a reason for why that is, and I'll just be brief with this, anything times 0 gets me 0. So 0 really has an infinite set of factors, as opposed to the number 1, which can only be achieved by doing 1 times 1. So since 1 is itself, it sort of breaks the whole definition of what a prime number is. A lot of people think that all composite numbers are even, or like any even number would be, but 2 is up here because 2 only works with 1 times 2. Now that's really quick because this should be review by this point, and if not, we can check out some. This is what prime factorization used to look like, but now it's going to look like something more complicated with variables. So just think about the number like 24, for example. If I had 24, I would break that into numbers that can be multiplied to get 24. I always try to start as close to the center as possible. Because of that, I wouldn't do 2 and 12. But what I would do are the choices 4 and 6, because those are very, very close to each other. And 4 would become 2 and 2, 6 would become 2 and 3, and I'd circle all of the dead ends of this. And by dead ends, if I had one that branched out earlier in the chain, I would have to circle that as well. And then normally you would write these out as 2 cubed times 3. A nice quick check on this would be to type that into your calculator, or you could be like 2 cubed is 8, and then 8 times 3 is 24. Now let's think of something outrageous like 400 that might seem like a real scary opportunity. But, here it could just become 4 and 100. 100 could become 10 and 10. 10 could be 2 and 5, and 2 and 5. But I wouldn't just stop it here, because this other end I can't circle, because that's composite, so I'd have to keep on breaking it down until all of the different values had been changed into nothing but prime numbers. So you're taking a number at a starting point and you're factorizing it, if you will, and you're turning it all into its factors, but those factors at the very end must be prime. In this example, since 2 showed up 4 times, I'd write 2 to the 4th, and then 5 showed up twice, and I write 5 squared. And you'll notice that these values are in ascending or climbing order. And if I type this in, I would do 16 times 25, and sure enough, you'd get something like 400. But this is what they're going to look like now, and they're going to be called, now you're going to factor these monomials completely. And since this is a little bit new, now is the point in the video where I might slow down a bit. Now here's how I'm going to do these. I have negative 12a squared times b cubed. So I'll just deal with the value of 12 over here. I'll turn that into 3 times 4, and then 2 times 2. Now, because these have values of variables in there, I'll sneak that negative 1 out front, just so I can more clearly see that, times the 2 I got, times the 2 I got, and then times 3. If you write these with 2 squared, I'm not really going to care. The only reason I didn't do it that way is because over here, the way these are shown is by separating a squared into a times a, and b cubed into b times b times b. So these problems, to be totally honest with you, are a little bit silly, a little bit unnecessary, and if you really blew through these quickly and had a solid understanding of them, it wouldn't be much of a problem. And if you're really wanting to write this as 2 squared, just back to that whole point. The reason you don't is because it's not like you can't, you have to leave these broken apart back here, like so the variables get separated. So should your factors as well. 38r squared. The more confident you are, like maybe you're like, well, I know 38 turns into 2 times 19. And I know that 19 is a prime number. But if you weren't sure of that, you could always just off to the side write 38, turn it into 2 times 19, because you're like, well, it's even, I can at least divide it once, and then show that work for that. But the whole point that I'm doing is, these side thoughts, these first steps, these things that aren't really showing up internal to my algebra, really shouldn't be written directly under the problem. I like to keep this work organized into the side. That's right, buddy. And that is the sound of my son who just turned 10 months old. R is just R, and then S is S squared, so I'm right times S times T. Hey, buddy. This problem is finished. That's it. One way you can check it is by, looking left to right and being like, well, 2 times 19 is 38, times R only shows up once. S times S would be S squared, times T would be just that T to the first power. Treat both of these problems as on your own problems, and I'll put answers up to them in a few seconds right about now. Pause this part of the video if you need to compare what you got with what I got. The greatest common factor is the greatest number that is a factor of both original numbers. And this little note here is if you have a couple of integers or two monomials that have a GCF of 1, there's a special word for what we call those things, and they are relatively prime. So that's just kind of a different sort of categorization. So if it's got a GCF of 1, they are relatively prime, excuse me. Alright, so here's how you define the greatest common factor. The areas of two rectangles are 15 square inches and 16 square inches respectively. Oh, by the way, that whole respectively word, that means like the first one they mention and then the second one in that order would be. So if they reference the first one again, it would be talking about the 15 size one. And then if they reference the other one after that, it would be the 16. So it's the order of things. It's a nice word when you're listing different things. The length and width of both figures are whole numbers. Okay, so there's your little clue. And these word problems in these chapters are kind of silly, but basically if it's a GCF chapter or section, you're probably telling yourself, I guess I should just take these two numbers and find the GCF. Put something on paper if it's a test or a quiz, and hopefully you'll get some points. If the rectangles have the same width, what is the greatest possible value for their widths? Well, there's a lot of ways you can do this, and one way is just by taking the numbers 15 and 16 and seeing all the different numbers that can go nicely into those choices. So we got 1, 3, 5, 15. And then just a little tip as you're doing these, it's nice to start on opposite ends, so I know 1 times 16 gives me 16, and then 2 times 8, and then 3 doesn't work, so I'll do 4 times 4. And once you hit that midpoint, you're pretty much done. And as I scan for numbers that agree, well, 16 and 15 don't agree, and so on. So where they share common factors are just 1 and 1. And this tells me that the numbers 15 and 1 are relatively prime, so the only way that I would get the same width going on here would be if they both were 1. So that right there is the greatest common factor, so since the value of the width, I guess, would be like width of 1, and then check your units on this problem, I would say inch. And not inches is singular, so width of 1 inch, or 1 inch, or whatever. Here's another real-world type problem. What is the greatest possible value for the widths if the rectangles described above have areas of 84 square inches and 70 square inches, respectively? And just to mix it up, we'll do this one a different way. We'll do it by, finding the prime factorization of both numbers. I look at this, I'm like, well, 7 times 10. So I'm starting here first because I have an easier time thinking about this number than I do the other. And then I got 2 and 5. So those are all the dead ends, and then 2 times 5 gives me 10, times 7 gives me 70. And that's just me walking my way back up the chain to verify that the original number is what we started with. I guess I could, if I wanted to, bother writing out the prime factorization of 2 times 5 times 7. If you don't want to, you don't have to. There I used time symbol just because a lot of the times these are old school type problems. Okay, so 84, trying to start close-ish to the center. 4 and 21 seems okay. So 4 times 21 gives me 84. 2 and 2 here, and then 3 and 7 here. And then when I write this out, I get 2 times 3 times 7. And if I wanted to, I could have this with a exponent, but on purpose I'm not going to. And then those are my dead ends. And if I walk those back, 2 times 2 gives me 4, times 3 is 12, times 7 is 84. And now that I have these written out, I can look at these and I can say, well, they both share a 2. And depending on where you noted it, you could run it back there. They both share a 7. And so I guess their greatest common factor between these two numbers would be 14. So as far as these ones, their greatest width would be 14 inches. And what that means is if I had, two different rectangles, maybe one would be a little bit shorter than the other, but they both would have a matching side of 14 inches. We could have done this problem the same way by listing this off. And a friendly reminder, if the greatest factor is 1, that tells you that they are relatively prime. So here's finding the greatest common factor of a set of monomials. And the whole purpose of this is that, there's no way we'll ever be able to factor something that looks like this if we don't start by factoring the beginning guys. So we're going to have to do these first. So now you don't want to have to show all the work on all these problems because it's just a little bit exhaustive. Now I look at 36 and I look at 54 and I think of what's the biggest number I could divide those by. Probably be like 18. So I'm looking first just at these numbers. And if I wanted to write all that out, I could. I could be like, well, hey, there's 2, 3, and 3 in one, and then 2, 3, and 3 in the other. And then if I multiply those numbers out, 2 times 3 gives me 6 times 3 is 18. If that felt rushed, then by all means, please hit me up. So I have 18. Now I look and I move to the next earliest letter in the alphabet, or maybe just what's furthest to the left. Now this has x squared, and that has x. So if I could pull an x out of either of those, I would. So out of x squared and x, they both would have just one x to share. And then moving on, I move over to the y. Well, this has a y. That has a y squared. So I could pull y from the left side, but not two of them. So I'd have to stop at 18xy. Just for grins, let's do this the longer way. So let's say I dealt with 36x squared y first. And I wanted to factor that out. I could look at this work here and I'd be like, well, it's 2 times 2 times 3 times 3 times x times y. Well, the other one, 54x y squared z, would be 2 times 3 times 3 times 3 times x times y times z. And so this first one is here and the second one down there. And I can map which ones match up. So this has a 2, that has a 2. This has at least 1 3, that has at least 1 3. And I can keep on going. And I move on to my x's and my y's, but I can't circle anything for the z. And if I scan through each of these, there's where 2 times 3 times 3 becomes 18. Here's where x times y becomes x times y. And if I look at the other guy, it's the same deal. 2 times 3 times 3 times x times y. But you really want to be to the point where you're not showing all that work. Like you can just jump right in. Let's see if we can jump right into this one. Now this one you can look at and you can be like, well, 22 in my head, I know that's only 2 times 11. I'm not looking at 32 because I know 32 has so many more choices. And by only looking at 22, I really can just factor out a 2 from that. because I know 2 fits into both 22 and 32. Now there's only one p, so I'm going to just pull out a p from this side, whereas if I pulled 1 from here, I'd be left with p times p, and there's that 1 going away. Then I move on to the letter Q, and I see Q on the left side, but not on the right side. So even though you might want to write Q down, that would be incorrect because both of them don't share a Q. I move on to R. Well, there's no R here, but there is on the other side, and the same deal for T, so that just doesn't work. So of all this problem, the only thing I can pull out as the greatest common factor is 2p. Now, if you want to, on your own, you can work out the whole problem the long way, and I'm going to show that work here. Working this out the long way, I have 2 and 2, p and p, but I really don't get to go too far before I'm completely done, because there's that 2p we agreed with, and then nothing else anywhere here matches up. Well, we had a little refresher of prime and composite numbers, and those are necessary tools because we need to pull those out from our leading numbers that are out front of these monomials. So just dealing with numbers like 24 and 400. Then we did monomials as we factored them out individually. Now we sort of cut corners later on when they gave us 2 that we wanted to find the greatest common factors between. And the reason we cut those corners is because you just don't want to have this much work shown to do every single problem like this. But do know that as I made these OYO choices, you should show these extra steps, if necessary, before you move on to anything else, because all of these chapters and sections in here build on each other. And if you don't have this down solidly, you'll be in a rough spot moving on to later ones. So that's why there's plenty of problems in here to get plenty of practice in, and these are factoring monomials.